So what happens is I had that problem for a while too until I realized I had been using OneNote for Office instead of OneNote for Windows 10 because I had a much older version of Windows 10. So I think if you go to OneNote for Windows 10, in the settings, Brad, I don't know if you can see this, but I think if you go something like, I think it's this is in Home. Oh wait, because this thing is full screen. I don't want it to be full screen. Uh, so if you go to Home, not Home, but it is in oh no, this is already a Windows OneNote for Windows 10. So I think here in View, you can just simply switch your background. Do you see this option for you, Brad? Do you see that option where you can switch background? Oh no. So what happens is that if you have that link, you are able to open that up in Windows 10, in the OneNote for Windows 10. So if someone provides you a link, huh, so you're not able to do that. So my understanding is here in the new notebook, um, you could add in a link that someone shared with you. So I think if you go to more notebooks, let me see. Huh, let me see. I have to double check that before I keep talking here because what happens is no one has ever shared a notebook with me. So actually, I've never had a chance to try that out. After the end of this class, I will try to do it, that way. Okay. Um, yeah. Hmm. Let me see. Oh, I see. The result is just seeing a wall of yellow highlight missing. But also, when I highlight it, you guys, I see. Huh. That's really interesting because what happened? Huh. Because I just did this with students in my other class, and no one ever mentioned that. That's very interesting. Huh. Okay. No, I understand your point. I'll look into this because there might be something different because the students in my other class, Transport 2, not a single person has mentioned that. And huh, I'll have to look into this some more. But I think right now, I think your primary interest is this Crank Nicholson thing. So let's focus on this Crank Nicholson thing, and then let's deal with this one. Let me get a chance to hack at it first. Okay. Yeah, I understand. Oh, Nat, so you also have that same problem? You also and you're not able to switch your background to black? So you're not able to switch your background to black? Uh, so so for example, do you see here on the side of the so you can switch it here? Do you see these options here on the side? Do you guys see the screen that I'm on my OneNote? I see. So you can switch it over when I copy yours to my OneNote. I see. So what do you mean by copy what? Copy the link? We can't edit the OneNote using uh, the link. I see, because the link I had sent to you guys is view only, no edit. Because can you imagine if I sent to you guys the original notes and you guys edited it or deleted something or changed something, that will affect the entire class, right? So I'll need to think of a way to do that. So I think I need to have two copies one version that we do in class, then after the class, I will freeze a version and share that. So I think I'll have to do two versions for this thing to work. Unfortunately, the semester is almost over. Yeah, well, next class. Okay, I'll figure this out for the next class. Okay, everyone's around now, so let's go talk about your questions. I know you guys have to have questions, so let's sort this out. Okay, I think someone had been asking me earlier about what do you call it? How many equations? How many unknowns? Does someone want to reiterate that question that you had asked me earlier? And then let me see, make sure you know I'm answering the correct question here. Was it Joshri? Was it you?
Yeah, hi.
Hi, I think was it you who was asking me that question earlier?
Yeah, I was. So I know how we were saying in the previous class that only the last temperature will be changing because it's staying insulated. So
Oh
I
no
just
no no!
wanted
It's
to.
so it's not, that's not the only one that's changing. I'm not sure I made that clear enough. But rather, what I meant is so if you look here, right? So if you look over here at these equations here, let me see if I can get this thing a bit more clear. Can you guys see this clearly or not? I know the yellow highlighting earlier that I had done is causing you guys some agony. I'll have to find a way to fix this problem for you guys. Um, so the primary thing that changes if you look at this, right? So all of these equations, right? All of these equations, right? Starting from the leftmost one all the way down to node 48 is all the same, right? It's just that this time around, you have an additional node down here, which is the node 49, right? The last one. That in the past, we used to specify that temperature, so it's not here, right? But this time around, it's going to be there. Okay. So this time around, you will have a temperature there. Okay. And so what happens is that this is that unknown temperature, right? So the temperature here would corresponds to this one here would be for the last one. That would be T49, I believe, right? So you'll have this one, which is for T49 down here, which you don't know, right? So notice if you look at that equation for T49, you're going to have this, and this negative r here should be multiplying the coefficient for T48 above it, right? Okay, right? So this thing stays at that one diagonal down, right? But this 1 plus 2r, you notice what happens there, right? What happens is that at minus r, tj plus 1, we said that tj plus 1 is going to be the same as the temperature at Tj plus 1 is the same as Tj. So this becomes a Tj. And so you end up with a 1 minus R. I'm sorry, 1 plus R instead of 1 plus 2R. And so what happens is this entire matrix here has an additional element, right? Because you have an additional variable. So the last element of this diagonal, instead of being 1 plus 2R, this is a 1 plus R, right? And above it, this one here, this negative R, extends right down here too, right, for the previous temperature. Do you understand what I'm saying here?
Yeah, that makes sense. So we still have three diagonals. This is the last temperature like row. That's when
Right.
it becomes 1 plus r instead of 1 plus 2r. So we just have to change the last part.
I'm just answering Abdullah's questions. So this is the previous notebook when we were talking, when this was the previous the previous class lectures. Okay. Um, so did that answer your question? Uh, Geoffrey?
Yeah.
Okay. So, see, the thing is, there's a bit of a balance here, right? Because what happens is, obviously, I can just do the whole thing out, code everything out, and then you guys can just do it, right? But see, I was getting a bit reluctant to do that. Okay, well, okay, fine. See, all right. Let's see. All right. So it's going to be something like this, right? So it's going to be something like this, right? And then so you're going to have, oh, how can we change only the last b value to include that? Oh yeah, I think someone had emailed me about that, and I had told them to ask me in class, so it stays fair. Okay, yeah, why don't I do that? I think this matrix thing here is okay. So let me answer this other question, which has to do with the coding. Okay. Uh, so it goes something like this. Let me move my face out of the way. Let's move this a bit more to the center. Okay, something like that. Okay. So let's import this stuff in. Okay. And so it goes like this, right? So let's say let's create a diagonal matrix, right? So let's say we have something like you know a is equal to numpy. Let's say it's an I, right? Let's say 5, something like that. So if you take a look at A, notice it's a matrix like that, right? And so your question was, you want to change individual elements, right? So notice, one thing we could have done here is, let's say if let's pretend all of these ones here was your 1 plus r, right? Well, all of these guys here was your 1 plus 2r, except this last one down here, you want to change that into 1 plus r only, let's say, or let's change that to, let's say, a 0.5. Then you just go something like this. You literally just assign it. So you go something like a, and then you want to get, in this case, you're after the last row and the last column, and you just set that to 0.5, let's say, to 0.5, right? And so now if you take a look at A, then you change that, right? But I think the other question was, well, what about B, right? So what about B? So it's the same idea. So you could have B, is equal to, let's say, numpy, I don't know, numpy once, let's say. Uh, let's say it's a size of 5, right? So let's say if you take a look at B, right, it's like that. Let's say you just want to change the last value, then you'll just assign the last value. Then you go -1. -1 is, if you put in a negative, you're coming in from the back, right? And you can assign that to, let's say, whatever you want, right? Take a look at B again. Then you notice you're changing just the last value, right? So if you look here, so if you look at our can, is it Canvas? Yeah, you see that video. So if you look at our course webs, where's that? Is it I think it's Canopy, I think. Let me see. Um, faculty. Oh my gosh. Ah, I don't have my device next to me right now, so this is going to be a pain. So let's not do this. But so what happens is, notice in the assignments, right? Oh, that is so annoying. So in the assignments, I said something like, first create your array of b values, right? So notice your b values here. You can create ones or zeros, your choice. You can say, oh, I'm just going to make a bunch of zeros, and then let's say right now, how many temperatures do you have? It's basically nx, right? Nx, the number of increments that you've made it, right? And but now, right, you don't know the last temperature you need to solve for it. So it's a -1 instead of -2, as it was in the notes earlier, right? And so what happened is all of the equations. So if you look here, oh, actually this is right here. Oh, why don't It's so tempting for me to just do it right here because it will be done in just like, I don't know, like 10 clicks. It's literally something like 10 clicks of a modification, right? So, if I can just give you guys a few hints, right? So the first place is obviously that has to change, right? That has to go to nx minus 1, right? And then this matrix here, obviously you cannot just go to nx minus 2. You have to go to nx minus 1, right? Okay. And then this one here, 1 plus 2r, right? You cannot go all the way to the end. It's fine. You can just go all the way to the end and then just change the last one there. So for example, in that case, you might just go something like, I know you guys would just, I mean, if I do it, it's just like as if the exam's over, right? It's kind of, I don't know, change the last one into a what? Into a 1 plus r. That's it. That's all you got to do. I'm not kidding you, right? As far as I got to erase it. Otherwise, I've just did the exam for you guys, right? And then for the B, well, what do? You don't want to go to minus 2. You only go to minus 1, right? And then what happens is, well, you see this guy here, right? So what's going to happen here, right? You see this expression here. So this expression here is true, right? For every single temperature, right? Except that here now for the last one, this one is going to be a little different, right? So let's take a look at our code here. Let's take a look at our notes, okay? Let me switch back to my this. Okay. Okay. So notice the key thing that's going to change here, right? So what's going to happen, right? What's going to happen here is for the last element, right? This is not the equation for the last element, right? Because what's going to happen is this guy here is going to be a Tj. So this is going to be a 1 minus 2r, right? And then also on this side here, this term over here, right? You don't have that, right? And so this term here needs to be added. Notice this is a minus. It needs to get added to the other side. Do you see? Okay. And so let's take a look, right? So if you look, go back to the code. Did I accidentally close my screen? No, it's here. Where did that go? Here. Okay. So notice currently, what are we doing here? So the last one here is, look at this. So we are subtracting r times t negative 1. Why are we doing that, right? Because currently, what are we doing? This expression here, right? So what happened here? So if you look here, right? So this last element here is modified from just the basic element, right? So you have a choice here. Maybe something that might be less confusing for you guys to do instead of doing something like this. One thing you might just prefer to just do that's easier is just simply go, it's going to be the same equation all the way except the last one, right? Did you see that? And then down here, you just simply type down your expression for the last one, right? Did you see? And so you could have, this is the equation, right? That's the expression to calculate the B vector for every single node except the last one. Then for the last one, it's a little bit different, right? So notice how is it different for the last one? What's going to happen for the last one? Let me copy that over, right? So for the very last one, let's see. You're going to have the one to the left. Oh, that's fine, right? And then instead of this one, what's going to happen here? We're going to get the current temperature, right? This one is not there. right? And there's going to be a 1 minus R, right? Why is that? Well, let's take a look here. So if you look back here, right? So if we are at the last temperature, right? So this is your T -1 corresponding to the last temperature, right? Notice you cannot go further than this. So this value here gets added into there. So this is the temperature for the last node. This is the temperature of the node 2 nodes back, right? So that's your -2, right? So if you look back again at the code, that's what we did there, right? So this takes care of those last two temperatures, right? And then what happens is over here, if you pay attention, what did I do there? So you notice here, this time around, we have this expression here. Did you see? Right? And so what has to happen here? Right? Notice this needs to get added to the other side, right? For that last temperature. So that becomes a plus R. And this is what this is. After that, it's at the same temperature, right? So this is going to be a plus R T -1, right? Because this is the same as that, and it's the same as that. So actually, this -2R is actually not there. And that's it. And so if you go back here to the code, if you look back here at the code, actually what happens is that -R is just not there, right? Because it gets added on again, right? Does that make sense to everybody? And you could do something like that. See, the problem is if I do this, you guys have, I just feel like you guys just haven't learned as much, right? Because the struggle, the spending some time to figure this out, that's actually how you learn stuff, right? And notice, that's all the changes you really have to do. And that's it. That was the exam. That's that's the exam. It's like 20 clicks. Okay. So yeah. Is there more questions I can help you guys with? Hi Elijah. You guys are not at the coffee house today. You guys are at home or somewhere.
Yeah, we're at my
We're
house.
at Kramer's house.
Oh, okay. Abdullah, you solved the exam for us. Well, dude, you better get this thing done, okay? You want this thing up, okay? Part 1 needs to be up already, okay? Yeah, any more questions? I can answer for you guys. Jared, any questions? This should help by deflated. What did I do wrong there? Well, I also got it to work using an extra position, a fictitious. Why were you discussing? You could do it, of course. Jared, yeah, you could definitely go ahead and add that on. Yeah, uh, you could. You could do that. Um, you could do that. Yeah, you could do that. There's if you do it that way, you just have to be a bit careful about other things. Like for example, not plotting that extra temperature, right? Of course, I know visually you'll never see it, right? But if you hang on to that, well, your bar is 1 unit longer, right? It's no big deal here, but you got to watch those things if there's a further calculation later on, right? Yeah, exactly. Well, you could add that on, except that you just have to keep in mind that that's a fictitious temperature. It's not part of the problem. And most importantly, don't go off and solve for that either, right? I'm not sure if there's many, 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 many ways to do this. Okay. Uh, yeah. Any more questions I could answer? Kate, I think last time we ended the class, you had a question. And I had told you I prefer to answer that question when everybody's around, to be fair. Kate, are you on today? I don't think you've ever missed a class, so I'm sure you're there somewhere. Any more questions? Okay. So if there are no more questions, I sure hope you guys will try to get. Let me see. What did you use to get that cool temperature gradient? What did I do? Um, oh, so what happens is, you know, I think Jared is into like the M&Ms now. Uh, so one thing you could do here is that when you add the scatter over here, you can go something like comma. You can set the color, right? And color is equal to something like RGB. And you can even set a transparency if you want, RGBA. So you can set your color, right? I'm not sure if it goes to 255. Yeah, so in this case, if I say something like, if I want it to be all red, 255, comma 0, comma 0, and an alpha, basically the opacity is full opacity, no transparency. So there. So if I do something like this, that's going to set the color to be all the same and all red, right? If in your case here, you want this color to vary with temperature, then you can make that into an F string, and then you could calculate that. So you have a braces, right? And you go off and calculate that 255. And then mentally, you kind of think, hey, my temperatures are ranging from what to what? And then you subtract that number from the 255. And so for every single plot, it's changing, right? So for example, you can get the temperature in the middle, right? Divide that by the expected temperature range, subtract the bottom, right? And then you could get something that varies in color. So there's so many cool things you could do there. You could do any kind of gradient, okay? Something like that, but you want to calculate a color channel, basically. You want to calculate, I hesitate to add those things in. So you can calculate a color for every single point. You realize that? So notice for every single X and Y value, you can have a different color if you wanted to. So you can actually just base it off on the temperature, in fact. So wherever the temperature is hotter, it's more redder. It's not just every single curve has the same temperature. Yeah, something like that. See, Jared's now beginning to have fun, right? Yeah. Oh, I was having fun yesterday too. So notice our setup is a bit different, right? So this green screen here, I decided to do that myself. And there's this, wonderful piece of code called OpenCV Python, right? So if you ever get into like that you begin to enjoy doing Python, then yeah, oh my gosh, feature description. I don't know, like you could object feature matching, uh, you know, something like that. Stuff like this. Is that cool, right? You got a picture, and that picture actually lies somewhere in an image or a video that you took. You can track that object as it moves within your image. So you could be holding on to like a picture, you walk around, you have the original picture, it tracks it where you go. Right? Is that cool or not? Right? No, chemical engineering gets boring once you start doing this kind of stuff. So yeah. Oh well, if there are no more questions, I'd really like to teach you guys some more on the heat exchangers. Is that okay? Or are you guys really mentally so focused up on the exam? Is that good? You guys?
I love heat exchangers, Carlos.
Because they're very important. And as I said, an exam is just an exam. Um, you guys take these exams way too seriously, and take the. Oh no, I got a problem here. Let me see. I got a problem here. Hold on for a second. I just realized I may not be able to open it. Oh. Let me see. I sure hope. Oh, phew. Okay. Let me see. Where's our? Because I literally got all of this thing working just like a few minutes before class, so I'm not as prepared today as I used to. I was like spending so much time trying to get that this green screen thing, this new setup to work. Um, Let me see. Okay, so let's go talk about our heat exchangers. Uh, yeah. Where is heat exchangers? Let's go to our things. So one thing, by the way, you guys should pay attention to is that this textbook has a lot of extremely useful chapters that we just don't have the time to talk about. External flow, internal flow, free convection. Uh, yeah, and especially if you guys ever get into like the solar cell business, right? Like radiation is ridiculously important in solar cells, right? Because the solar the radiation from the sun that does not get converted into electricity gets converted to heat. And so what happens is that and there's no solar cells that's perfectly efficient. So what happens is that your solar cells get hotter and hotter, and their efficiency goes down with increasing temperature. So actually, one element of solar cells is actually keeping the solar cells cool enough and not having them overheat. Okay, so there's a bit more to that design. Actually, it's not just simply that you have to have some means of keeping the solar cell cool. Um, so let me see. So 706. Okay, so let's go to about page 706. Yeah, so somewhere here. Okay, so let's talk about heat exchangers. All right, so right now I'll just be your tour guide. So let me zoom this thing in. No, that's not what I want to do. Uh, how do I zoom this? I think it's just this. Yeah, okay. All right. So let me get myself out of the way. Maybe I'll go. I don't know where I want to be. Maybe I'm just gonna go over here. Okay. Ah. Okay. So where we need to go here is at the end of that last class, what happened was Jared had some really good questions about, wait a minute, at the start of this whole thing, I mentioned to you about this entire difference between co-current and counter-current heat exchangers, right? And so the question becomes, how does this connect to what we have been doing in class uh, with the as far as the equations go, right? Let me see if I got come over here. I am not a gamer. My mouse control is so horrible. Mm, I just want to resize this screen. Let me zoom this out a bit, okay? All right. So now I have a place to write. Transport one, shell and tube, okay? All right. So at the end of the last class, Jared was basically asking me, "Hey, how does this connect back to the discussion, right? So what happens now?" So notice at the end of that last class, we had this expression there, and let me rewrite that again cleanly, right? So if I were to rewrite that cleanly, we have Q is equal to uh, what happened here? That's really strange. Okay. So we had some sort of overall heat transfer coefficient. This is your U. And the value of U is what? You might remember for water to water, that's about 1,000. Uh, Andrew, oh, you're just joking. Okay, and then so you got the overall heat transfer coefficient. So that's about 1,000 for water to water, and for water steam, that's about 3,000. Okay. Um, and on Monday, I'd love to talk some more about this. Okay. And then so what happens? So this is characteristic of your device. So you might ask, hey, if I increase the flow rates of the water, uh, if I increase the flow rates here, right, in the pipes that are flowing, does that affect the value of U? Yeah, it does, definitely it affects the value of U. It affects the heat transfer coefficients, right? But you might also ask, if I increase the flow rate, what is the biggest effect? Does it really change my value of U a lot? Well, it changes it somewhat, but once it's turbulent and it doesn't change too much anymore. But if you adjust the flow rates, what it really changes are these heat capacity rates. Because remember, those things are flow rates multiplied by heat capacity. So if you change your mass flow rates, it changes those values. Changing the mass flow rate will also have an effect on U. But what's going on here? Hmm. I'm not going to use Google Chrome anymore. I don't know what's going on with Google Chrome today. I'm sorry about that. Let me see. I think let's give up and let's open it up in Microsoft Edge. Okay? And I think Microsoft really wants us. What now? Yeah, no thanks. I don't care about this. No thanks. All right, here. Let's try Microsoft Edge. Okay, somewhere here. Why is this thing so hard to use? I don't want Microsoft Edge as my default browser. Okay. I hope this doesn't crash anymore. All right. Okay. So back here. So this U value, right? Your overall heat transfer coefficient, it involves your heat transfer coefficient, the individual H values for the inner, for the inside, the H for the outside, and as well as another sort of resistance to heat transfer associated with, let's say, the thermal conductivity of your material of the shell wall, and also, let's say, the thickness, and also the thickness of your walls, right? Of that pipe that's separating the inner and outer pipe, the inner and outer flow. So the thickness of that pipe essentially there. Okay. And then the next thing is you have this area. And this area, of course, is the common area, right? That is shared where the two flows have an opportunity to do a heat exchange. And then the next thing is we said that over here, there's some sort of a mean meaning to say some sort of an average, right? At the end of the last class, I was mentioning something like if you had two numbers, let's say A1 and A2, right? In high school, if you want to take the mean, you always have only one mean, which is the average, right? A1 plus A2 over 2. That's your arithmetic mean. And then you guys had probably also learned something like a geometric mean, right? That is a geometric mean. But what happened is there's yet another type of mean, which is something called a logarithmic mean. So there's a log mean. And this idea of a log mean is something that's actually more general. It's not just in heat exchangers. So for example, you'll see something like this in transport 2 when we talk about log mean partial pressures, for example, or partial pressure difference, partial pressures. So a log mean would be something like A1 minus A2 divided by natural log of A1 over A2. So if you have two numbers, the log mean is that. But notice that in this case here, we are taking the logarithmic mean of the temperature difference at position 1 and the logarithmic and the temperature difference at the other position, right? So if you look here, we need to know the temperature difference on one side and the temperature difference on the other side, right? And so thinking about it that way, so we say it's a log mean temperature difference. So we have our temperature difference at one position, and then we have our temperature difference at the other position, divided by the natural log of the ratio of the two temperatures, okay? So now naturally the question comes in and says, hey, how do things change whether we have co-current or whether we have counter-current? Well, the way it works is the following, right? So if you had a co-current, So let's say if you had let's just draw it like this. So if you had a co-current and this was your hot stream and this is your cold stream, right? And let's call this position 1 and this thing is position 2, right? So notice how this thing will look like. Your delta T at 1 will be the temperature of your hot stream inlet minus the temperature of your cold stream inlet. The delta T, the difference in temperatures of the two streams at the other side here will be equal to the temperature of the hot stream outlet minus the temperature of the cold stream outlet. So this thing would be the case of co-current or parallel flow. That's the way the textbook refers to it. So if you have a co-current situation, all you need to do is you just merely have to express your temperature difference at the two locations in this way and put it straight into that equation. And it gives you the correct answer. That will be the heat exchange for a given heat transfer, overall heat transfer coefficient and area. Now, if you repeat it, let's say you go off and flip the geometry. So you go off and not flip the geometry, but you just simply flip your connections, right? So this time around, you have a hot stream going in here and you have cold stream going in there. Well, this is still at position 1. This is still at position 2. Now, what happens here is that your delta T1 is going to be what? Notice it's going to be the hot stream going in minus, well, this is now the cold stream out. And then you'll have delta T2. And this time around, this will be the temperature of the hot stream. Well, that's what's going out. So outlet minus the temperature of the cold stream inlet. And in this case here, the equation for calculating the heat transfer stays exactly the same. No difference. Does that make sense? Okay. Cool. Jared, we good? Everybody good with that? Jace? Okay. Yeah, so that's it, right? So now you might ask, well, at the start of this class, I made a big fuss about like how one is better than the other, right? Okay, so let's think a bit about it this way. So this might be how the counterflow heat exchangers. Notice that if you have it going counterflow, look at it. Your hot stream goes down in temperature. In the temperature of the cold stream, the temperature that comes into there is entirely at your control. You can set whatever temperature that's going to go into there. That's the inlet temperature of the cold stream. The outlet's temperature here, of course, there'll have to be an energy balance, right? Okay. So either if you set the hot stream inlet and you set the cold stream inlet, and you put a specification and you say, hey, I want my hot stream outlet to be this certain temperature. And if all the flow rates are fixed, then you don't have control over this anymore. One of those variables is governed by the energy balance. Okay. So compare this scenario here to this scenario here. So this is the case of a co-current, right? So did you notice what happens here in the case of a co-current, right? Notice what happens in a co-current situation is that your temperature of the hot stream, right, cannot get to the temperature of your cold stream because your temperature of the cold stream goes up, your temperature of your hot stream goes down. You always meet at somewhere in the middle, right? You're meeting somewhere in the middle, and as you go along your heat exchanger, the temperature differential keeps decreasing until farther down, basically you're just wasting heat transfer area. You have more area for heat transfer, but what happens is that the two temperatures have basically converged together and you no longer have a driving force for heat transfer. You contrast this in this situation here, for example, right? So notice what happens here, right? Notice the other thing that you notice is that the hot stream outlet temperature, right? This hot stream outlet temperature, right, can actually get below the cold stream outlet temperature. So this cold stream outlet temperature can actually be higher than the hot stream outlet temperature. Did you see? Right? So you could have easily a situation, something like this. So if you have a counter current flow situation, right? So if this is a counter current flow situation, right? So if you're plotting temperature versus area, right? On one side, let's say you have your hot stream, right? So this might be your hot stream temperature, right? And so hot streams coming in and going out there, right? You have your cold stream temperature. Your cold stream temperature might be here, and it might go something like that. Okay? And so this might be your cold stream temperature. Notice the interesting thing that happens there is you notice the outlet of your hot stream, right? The outlet of the stream that you have cooled down can actually be lower than the temperature of the cold stream after it has left, right? And it's pretty obvious. You'll notice here there's more overall, a bigger delta T on average. Okay. Any questions about this? This is fairly straightforward. Okay. So let's scroll some more. So now let's look at some temperature profiles, and let's see if you could, just by looking at these temperature profiles, make a few statements. Okay. So let's take a look at this guy here. So, someone tells you, hey, in your heat exchanger, the temperature profiles look like that. Well, you notice that when you see something like this, well, what do you notice? One of the temperatures, the hotter temperature stream, right? Notice this is the one that is at a higher temperature. Its temperature stays constant as you go along the heat exchanger. What does that mean? Well, there's two possibilities there. One of them is that you got a phase change situation, right? Let's say if you have steam that is condensing. Notice that the temperature, the bulk temperature of the steam that is condensing, that is entirely governed by what? That is, in that case, governed entirely by Antoine's equation, right? So if your heat exchanger, where the steam is on the outside, has a certain pressure, right? Well, it's at that pressure, it's going to set the temperature where it's going to condense, right? So in that case there, the outside temperature, right, of your shell is going to be set by the pressure of your heat exchanger on the outside, right? Antoine's equation. Alternatively, if you think about it, you got a heat exchanger, right? And you got a massive honking flow of hot water, right? And then on the other side, you have just a very little amount of cold water. Well, you notice there's so little cold water that's flowing that it cannot even really change the temperature of the hot water, right? So in this situation here, you have such a massive flow of hot water or of the hot stream that its temperature, because notice CH, that is a heat capacity rate. So it is the heat capacity, right, multiplied by the mass flow rate of the hot stream. So that if that's much bigger than the heat capacity rate of the cold stream, then the temperature of the hot stream barely changes. Now, in this other situation there, you got exactly the opposite situation, right? So in this situation here, notice it's your cold stream, right? That's going to have a massive, much, much higher heat capacity rate. Or notice in this other case there, it says there is an evaporating liquid. Okay, so you might ask, evaporating liquid. Can you think of a scenario, something like this? What might be evaporating in your heat exchanger, let's say? There's so many, many possibilities. So, yeah, a cooling tank. Well, usually a cooling tank. A bit more specific, Sam, about what you mean by a cooling tank. Uh, there's just so many scenarios. Let's say, like some plants have big, cooling towers. Oh my gosh, that boil off water. Yeah. So Sam, so what happens is just a few comments there because you said something there. Okay, so be somewhat cautious about the word cooling tower. Okay, because the cooling tower is actually it's a very serious unit operation in chemical engineering, right? It's when you say cooling tower, people are very specific exactly what that means. Okay, so if you have a situation where you're cooling something down and it's a tank, don't call it a cooling tower. Okay, isn't that well, see, actually, what is so interesting since you brought that up, actually, what happens is, oh, can I? Oh, shucks. Let me see. I can do something like this, actually. Hold on for a second here. I apologize here. I don't know if this is going to cause me a problem. Do you guys still see me and still see everything, or did this cut it off? Can you say something? Because I switched screens, so I cannot see quite
I
what I'm
see
doing
you.
anymore. You can still see me? Okay.
Yeah.
Good. So what happened is I switched desktop to my laptop, which is linking to my son's computer. So I apologize there for a second here because I need to grab something in response to that question. Because I actually had just let me see. Let me just download this. Okay. And then where did this go? Let me move this. Okay. Let me switch back now. Okay. Okay. So I think I'm back. And then now I'm going to open this file. Let me see. No, let me see. It's not here. Let me get this out of the way. I just have so many windows open. This PC, it's in downloads. Okay, good. Yeah, I think that's it. Let me see. Oh, there you go. Hey, uh, so so for example, if you were actually taking my Transport 2 course, right? If you're taking Transport 2, this is their final exam. So you guys have an exam, right? And if you take Transport 2, I think the environmental engineers are not required to take Transport 2. But if you do take Transport 2, we actually, our exam 2, our last exam, is actually a cooling tower exam. Did you see? And so clearly, when you see that, I mean, let's read through it a bit. Right? I see. Okay. If you look at that, hey, you have a cooling tower, you have a cross section, you got the diagonal slats, and there's water that's flowing down, right? So it's literally, you could think of that as you got a bunch of diagonal meshes in there, and you spray water down. The water's flowing down like all these like waterfalls, right? And you got air, right? That's blown from below. And what happens is that the water evaporates, and the evaporation of the water cools down the water, right? Because the enthalpy of vaporization of water is very high. So if you evaporate the water, it cools down the water, right? And this is actually how cooling towers are done. So every time you're driving by Martin Luther King and you see the power plant for UC, the one that generates UC's electricity, and you see billows of steam or like fog or clouds coming up that plant, right? That's a cooling tower. And the reason you see all that steam, or more like fog, actually, it's not steam, it's like fog coming out. That's because they are evaporating water with air to cool down the water. And that's actually a cooling tower. The mechanism of this is actually quite very different from heat exchangers that we are talking about. Okay. But that's where you might end up going to if you took Transport 2. Okay. So that's not quite the situation that we have here. Where did that go? Is it this? No? Is it this? Yeah, okay. So, well, let me see. So Owen, my plant, okay, had a tower that had a lot of layers that let the water recondense and recycle back into our system. Uh, uh, so that I'm not sure that will be referred to as a cooling tower. You might be. So when you say water recondense, so basically steam comes back, right? So it's basically you have a steam plant, right? And it releases high pressure steam. Some of that steam comes back as low pressure steam that has a lower qualities mixed with liquid water, right? And what happens is you want to condense all of that steam back. Is that right, Owen? Yeah. So usually, did you really, really recondense that water? Or did you just feed that water back into the boiler? Because I would be thinking that if you get out of your way to purposely cool down the low pressure steam that has returned, then that's kind of like somewhat wasteful unless there's a specific reason for doing that, right? Did you guys really purposely cool it down? And also, when you say a lot of layers, can you be a bit more specific what you mean by a lot of layers? What do you mean by a lot of layers? Are you meaning, is it a heat exchanger? Yes. So are you quite rather certain that those layers are condensing the water and not actually heating it back up? Because that would be my gut instinct that initially that's actually the water that has come back. You're actually reheating it back up to send out rather than actually purposely condensing it. Although that's possible. I'm not so sure about the details of your system. Yeah. Was opened. Okay. I'm a bit confused by uh, by that now. Uh, let's talk after class. Okay. Yeah. Uh, yeah, because it's without going into you notice how if you have one of these questions, really it takes a lot of detail before it's possible to really talk about it in an engineering way in the format of a classroom. Okay, so let's talk after class. Okay, otherwise it's such a, as you said, loaded question with not enough details to really pry into. Okay, so well, let's think about something simpler. Okay, so if you focus on something simpler, let's say, can you think of a situation uh, where uh, where you had something like this? So can you think of something like that? So a simple a fairly simple example that I might just think of is let's say if you have something, let's say acetone, let's say uh, we probably better not use acetone there. So let's say you have it on the outside, right? So let's say you have hot water. It probably will not be hot water, but I'm just no one would really do a process like this in real life. So the hot water goes out, right? And then what happens is maybe you might have on the outside you have let's say uh, you have methanol, right? Or let's say acetone or something with a lower boiling point, right? And so what happens here is that you might then have a big exit, right? And this might be methanol vapor, CH3OH vapor, right? So you might have a vaporizer, right? So in this situation here, you have liquid methanol that's going in, and you want to vaporize it, right? And you would pass, let's say, hot water. It's enough, right? You put in hot water, maybe 90 Celsius, it's not 80 Celsius, and you get it out. And what happens is that the methanol vaporizes. So in this scenario here, then your water is going to go down in temperature. The methanol here is boiling, right? So at the given pressure here, if you set the pressure there, if let's say the pressure at the exit is let's say 1 atmosphere, then this temperature here that you're going to get for the methanol is going to be limited to the boiling point, to the normal boiling point of methanol, right? And then now, of course, in this other scenario here, where both hot stream and cold stream decrease or change in temperature. Well, in this case here, their heat capacities are roughly similar, right? And so what happens is it's quite evident, and this is an element of common sense, that if you see one of these plots, that you immediately know which one is which one has a lot more of. Basically, the stream, right? The stream that has a smaller temperature change is the one that usually has a much higher heat capacity rate. Most fluids have comparable heat capacities. So if you have liquids and liquids, right, on a per density basis, their heat capacities are fairly similar, except, of course, for the ones like water, which is hydrogen bonding. But even in those scenarios, it's only maybe about a factor of 2 or so more than compounds that do not hydrogen bond. But in those scenarios here, you can get a rough estimate of which one has a much higher flow rate than the other. Okay. Yeah. So let's keep. So here's some worked out examples. They actually plug in numbers and see, right? Now you notice, right, when you look at this scenario here, notice the way we have set up this calculation. Think about it this way, right? Is this set of calculation here works as follows. If you know the LMTD, log mean temperature difference, you're able to get the amount of heat that gets transferred. But notice if you think about it the other way around, in which I say, I need to transfer so much heat, right? Okay, and then this is the area, this is the heat transfer coefficient. Tell me the temperatures. Notice that in that expression there, you have that logarithm, right? So it's a somewhat a bit more of a nonlinear equation that you need to solve. It's not that difficult, right? But later on, what happens is that, of course, a shell and tube heat exchanger, single pass, that's not the only type of heat exchanger that we looked at. That's actually going to be a fairly rare heat exchanger. Most heat exchangers are multiple shells, multiple passes. That's the more typical heat exchanger. So what do I mean by that? Well, most heat exchangers that you purchase or are installed are more akin to this type of a heat exchanger, something like that, right? Or maybe something like that. And so you might ask, wait a minute, Carlos, you had just taught us how to do the analysis for just a shell with a tube with a shell, countercurrent, co-current. And then you're telling me now that most heat exchangers are actually of this more complicated design. How do I deal with that? And the answer is the details of those calculations are obviously a lot harder. And some of those have to be done by experiments, in fact. Okay? But we stick with what we have. That's this simple geometry, right? And then I'll show you a method which is called the NTU, net transfer units effectiveness method, effectiveness efficiency method. And that we calculate those ones for our regular shell and tube heat exchanger. And then we rely on what other people have done who have solved these equations, right? And offers us a convenient way of designing heat exchangers in that manner, okay? So once you see the detail, it becomes more clear what exactly I mean by that, okay? So let's come here, okay? So, okay. So let's read a bit about this, okay? So this is kind of like what I was saying. So the LMTD, okay? So of course, if you guys are in an interview, what do you know about heat exchangers? LMTD, okay? So it allows you, right? So if when you know the fluid inlet temperatures are known and the outlet temperatures are specified, right? So if you know the inlet and you say the outlets, well, that means you know Q, right? Oh, is it 12:46 already? Oh my gosh, time flies. Oh well, so get that exam done ASAP. Please do not wait till the last minute and to start uploading and then emailing me about all sorts of problems that you're going to run into. Because as you know right now, like I'm ridiculous, almost extremely forgiving profile, let you go off with any excuse. But please don't do that. Okay, so let's just get it done ASAP. Okay, so get it done. Please don't wait till the last minute, please. I'll hang around if you guys have any questions. I don't have any particularly important thing to go to right now. So, any questions?